MXenes, synthesis, properties and emerging applications of two-dimensional transition, metal carbides and nitrides. The emergence of two-dimensional 2D materials has significantly transformed modern materials science because of their exceptional physicochemical properties and broad technological relevance. Following the discovery of graphene, extensive research has focused on layered materials such as transition metal dechalcogenides, boron nitride, graphitic carbon nitride, and layered double hydroxides. Among these advanced nanomaterials, MXenes have attracted exceptional scientific and industrial interest due to their metallic conductivity, tunable surface chemistry, hydrophilicity, and mechanical flexibility. MXenes are a family of two-dimensional transition metal carbides, nitrides, and carbonitrides generally represented by the formula Mn+1xNtx, where M denotes an early transition metal such as titanium, niobium, vanadium, molybdenum, chromium, or tantalum, and X denotes carbon and/or nitrogen. Tx refers to surface terminations including oxygen, hydroxyl, and fluorine groups. MXenes were first reported in 2011 by Yuri Gogotsi and Michel W. Barsoum through selective etching of aluminum from Ti3-AlC2 max phase using hydrofluoric acid, HF. Since then, MXenes have become one of the fastest-growing classes of 2D materials because of their unique combination of electrical, thermal, optical, catalytic, and electrochemical properties. Crystal structure and synthesis. MXenes are generally derived from layered max phases, which are ternary carbides or nitrides composed of transition metals, A group elements, typically aluminum or silicon, and carbon or nitrogen. In max phases, strong metallic covalent M-X bonds coexist with relatively weaker M-A bonds. Selective removal of the A layer generates atomically thin MXene sheets with expanded interlayer spacing and functionalized surfaces. MXenes possess a layered hexagonal structure, in which transition metal carbide or nitride layers are stacked through van der Waals interactions. Surface terminations such as hydroxyl, oxygen, and fluorine strongly influence their electronic structure, conductivity, hydrophilicity, and chemical stability. The interlayer spacing can also be tuned through ion or molecule intercalation. For example, cationic surfactants have been reported to increase the interlayer spacing of Ti3C2Tx by more than 170%, thereby enhancing ion transport and electrochemical performance. Top-down synthesis. The most widely used MXene synthesis strategy is the top-down selective etching of max phases. Initially, concentrated HF was employed to selectively remove aluminum layers from Ti3-AlC2 to form Ti3C2Tx nanosheets. Although effective, HF poses substantial safety and environmental concerns because of its highly corrosive and toxic nature. To overcome these limitations, safer in situ fluoride etchants, such as LIF and HCl mixtures, were later developed. In this method, LIF reacts with hydrochloric acid to gradually generate HF, enabling controlled etching and easier delamination of MXene layers. Organic intercalants and ultrasonication are often subsequently employed to exfoliate multilayered MXenes into few-layer or monolayer nanosheets. Recent advances have focused on fluoride-free and environmentally benign synthesis approaches, including molten salt etching, electrochemical etching, alkali-assisted etching, and water-free organic solvent methods. Molten salt etching offers high selectivity and reduced structural damage, while electrochemical etching enables scalable and controllable MXene production with lower chemical waste. Bottom-up synthesis. Bottom-up synthesis approaches directly construct MXenes from atomic or molecular precursors. These methods include chemical vapor deposition, CVD, pulsed laser deposition, PLD, sputtering, hydrothermal synthesis, and pyrolysis. CVD-based methods can produce highly crystalline ultra-thin films with controlled thickness and fewer structural defects compared with chemically etched MXenes. Similarly, PLD and sputtering provide excellent control over film composition, crystallinity, and uniformity for electronic and optoelectronic applications. Although bottom-up approaches remain less mature than top-down synthesis, they provide important opportunities for defect engineering and precise structural control in future MXene technologies. Structural and physicochemical properties. MXenes exhibit a unique combination of structural, electrical, optical, thermal, magnetic, dielectric, and catalytic properties arising from their layered architecture and tunable surface chemistry. Structural and morphological properties. The layered morphology of MXenes provides exceptionally high surface area and abundant active sites for adsorption, catalysis, and charge storage. MXenes may exist as monolayers or few-layer stacks, and their lateral dimensions can vary from nanometers to several micrometers depending on synthesis conditions. The distribution of surface terminations significantly affects conductivity, hydrophilicity, and chemical stability. Oxygen terminations may lower the Fermi level and induce semiconducting behavior in Ti2CO2, whereas fluorine terminations tend to preserve metallic conductivity. Defects such as vacancies and grain boundaries further influence electron transport and mechanical strength. Morphologically, MXenes often exhibit an accordion-like layered structure after etching and delamination. Compared with graphene and reduced graphene oxide, MXenes generally display superior hydrophilicity and comparable or higher conductivity. Lower HF concentrations and shorter etching times have also been shown to reduce defects and produce larger flakes with improved electrical conductivity. Electrical and dielectric properties. One of the most remarkable features of MXenes is their high electrical conductivity. Ti3 C2TX can exhibit conductivity values exceeding 10,000 Siemens per centimeter, making MXenes among the most conductive solution-processable 2D materials. Their conductivity strongly depends on transition metal composition, surface terminations, and interlayer spacing. Intercalation of ions or organic molecules can increase conductivity by facilitating charge transport between layers. Surface modifications through thermal or alkaline treatment can also significantly improve conductivity by altering functional groups and removing trapped species. MXenes additionally possess high dielectric permittivity due to their layered metallic structure and high electronic density near the Fermi level. Their dielectric properties are frequency-dependent and can be tuned by surface functionalization or interlayer engineering. These characteristics make MXenes promising candidates for capacitors, electromagnetic shielding materials, and energy storage devices. Optical and magnetic properties. MXenes exhibit strong broadband absorption spanning ultraviolet, visible, and infrared wavelengths. Their optical response is associated with surface plasmon resonance, where free electrons oscillate collectively under electromagnetic radiation. This phenomenon is highly advantageous for photothermal therapy, surface-enhanced Raman spectroscopy, biosensing, and optoelectronic devices. Photothermal conversion efficiency is particularly important in biomedical applications. Under near-infrared irradiation, MXenes efficiently convert absorbed light into heat, enabling cancer photothermal therapy and antibacterial treatment. The magnetic behavior of MXenes depends primarily on the transition metal species and surface terminations. Certain manganese-containing MXenes exhibit intrinsic ferromagnetism, whereas others may display antiferromagnetic or paramagnetic behavior. These tunable magnetic properties offer potential applications in spintronics, magnetic sensing, and data storage. Mechanical, thermal, and chemical stability. MXenes combine high stiffness with considerable mechanical flexibility. Single-layer Ti3C2Tx exhibits a Young's modulus of approximately 330 gigapascals, comparable to many advanced 2D materials. Their layered structure allows interlayer sliding, which contributes to flexibility and mechanical resilience under repeated deformation. MXenes also exhibit strong interfacial adhesion with polymers and ceramics, making them highly suitable for composite materials and flexible electronics. Their high impact resistance and fatigue stability are beneficial for wearable sensors, protective coatings, and structural monitoring systems. Thermally, MXenes demonstrate high intrinsic thermal conductivity, typically in the range of 30 to 50 watts per meter per Kelvin for Ti3C2Tx. Their low thermal expansion coefficient and high thermal stability make them attractive for thermal interface materials, aerospace components, and heat management systems. However, oxidation at elevated temperatures in air can lead to the formation of metal oxides, such as TiO2, affecting long-term stability. Chemically, MXenes remain stable in acidic environments because of strong metal-carbon or metal-nitrogen bonds. Nevertheless, oxidation in humid air remains a major limitation, particularly for titanium-based MXenes. Encapsulation, antioxidant treatment, and inert atmosphere storage have therefore become important strategies for improving long-term stability. Applications of MXenes: energy storage and supercapacitors. Energy storage is among the most extensively explored applications of MXenes. Their high electrical conductivity, layered architecture, and pseudocapacitive behavior enable rapid ion transport and excellent charge storage capability. MXenes have demonstrated outstanding performance in supercapacitors, lithium-ion batteries, sodium-ion batteries, and zinc-ion batteries. MXene-based supercapacitors exhibit high volumetric capacitance, rapid charge-discharge rates, and long cycling stability. Their performance can be further enhanced by integrating MXenes with graphene, carbon nanotubes, conducting polymers, or metal oxides. Electromagnetic shielding and electronics. MXenes are highly effective electromagnetic interference (EMI) shielding materials because of their metallic conductivity and dielectric loss properties. Thin MXene films can absorb and dissipate electromagnetic radiation, protecting sensitive electronic systems. Their flexibility and conductivity also enable applications in flexible electronics, wearable sensors, transparent conductors, electronic skins, and neuromorphic computing devices. Catalysis and environmental applications. MXenes possess excellent catalytic properties because of their high surface area and tunable active sites. They have demonstrated activity in hydrogen evolution reactions, oxygen evolution reactions, oxygen reduction reactions, photocatalytic degradation of pollutants, and CO2 reduction. In environmental remediation, MXenes effectively adsorb heavy metals, radionuclides, dyes, and organic pollutants from water. MXene membranes also exhibit high permeability and ion selectivity for desalination and filtration technologies. Biomedical applications. MXenes are increasingly investigated for drug delivery, bioimaging, antibacterial coatings, and photothermal therapy. Their hydrophilic surface and tunable chemistry enable efficient biomolecule interaction and controlled drug release. Furthermore, their antibacterial activity makes them promising for medical coatings and implantable devices. Challenges and future perspectives. Despite remarkable progress, several challenges remain before the large-scale commercialization of MXenes can be realized. Key limitations include oxidation, instability, environmentally hazardous synthesis methods, difficulties in large-scale production, and challenges in controlling surface chemistry and defects. Future research is expected to focus on fluoride-free synthesis, oxidation-resistant MXenes, heterostructure engineering, and multifunctional composites. Advances in additive manufacturing, artificial intelligence-assisted materials design, and scalable processing technologies are likely to accelerate the development of MXene-based energy, environmental, and biomedical systems.